All right, it's time again for Science to Make You Happy, the podcast series where Cybernetica tells you about new technologies related to security, but not only. Today, we're talking about trusted execution, a technology with many other names, which you will hopefully learn soon. With me today, Armin Kisand from Cybernetica, working as a software architect. And as far as I know, you've been working with this technology for quite a while now, since I don't know how many years.
7.5 years. So,
in trusted execution land, I think it's quite a while, no? Because the technology, at least in general, software development, isn't that much older.
It depends on what trusted execution environment technology you are looking. The one which I've started working at or on was Intel SGX, or just one specific TE technology, trusted execution environment technology, and this started, I think, 2015 or 16. So it was at the time bleeding edge. And but if we look at other options, then what everyone probably of our audience has in their possession, a phone. Then on Android phones, for example, there is also some trusted execution environment technology, which is a lot older. So I think to recall something that the first mentions of it were 2002 or something. So anyway, it's not ancient, but it's not super bleeding edge anymore. So depending on what trusted execution environment technology you're looking.
So today, especially engineering will make you happy. But first of all, before we start explaining what trusted execution is, I think we need to first tell people some uncomfortable truths about computers. And first of all, well, people know that cybersecurity is a thing. And I've always been telling the story that I believe cybersecurity is a thing because we invented computers the wrong way initially. We made computers so that information would be super easy to copy, so that communication would be super easy. And then we started putting in restrictions and controls later. At least that's sort of been how I've explained things. So let's think about software and computers for a moment. So why are we calling this new technology trusted execution? Are normal computers untrusted?
Yeah. Interesting point to take it. Interesting take. So when you take your phone, probably the regular user, my mother, she doesn't know what the phone does. She can tap it and she can use it, but what actually happens in there, it's just basically a big black box, or a tiny black box. And at home, I think the other extreme, what I have, the only thing where what I fully trust, because it's just so dumb, is a very old calculator that I have. But everything else is very, very smart, and you just can't realistically in a human lifetime go to the hardware level, go through the operating system level, go through the software level, and verify what you are actually having in your hands and running. And trusted execution environments, they try to improve the situation, that you can be more confident on what software you are actually running, and leaving out a lot of the surrounding software and hardware components, which make up your device, and to basically improve the security posture and security story.
Mm-hmm.
Yeah.
That's we'll get back to that a little bit more later on how this improves the story. But again, I think we need to explain to the listener a bit more. If let's take this phone that me or you or our relatives are using, they expect that if I press a button, then something happens. And if I press a button and something shouldn't happen, it doesn't happen. So security and safety are sometimes defined as predictability, that I know what will happen if I press a button and only the intended things happen. So the thing is that if I talk to a software service through my app or on a website, then I can't really check what's going on the other side, right? Because
so yes, when you're just using your phone, then the phone just when it if you're talking about back-end services or some service which runs on the internet which your phone is connected to, then usually just there is just how to say data transferred, which is it's protected in a way that that nothing on the network can access it, but otherwise you don't really know what is done with the data which is exchanged on the back end. So you just you exchange data and hope that the data is used in the way as it's written in the end user license agreement or whatever, in the general terms and services. Or how the service provider claims to use your data. And so maybe staying with the phone example, maybe I add some other nice thing I found out once. So in Germany there's the Chaos Computer Club, and they wanted to check whether the Android phone or some phone, which I think it was an Android phone, actually is just doing what it says that it does. And the main question was whether phones are like listening on us, whether they are spying on us. And so they took the phone and then put it into some shielded room or some room where they could check all the connections when it's talking to the internet, and check whether when someone is talking in the room, whether the device itself becomes more chatty, transfers data to the environment and so on. And so they really made a deep dive on how the device behaves to understand whether the device is trustworthy and does what it's supposed to do and does not what it's not supposed to do. And the important thing is that you can do this if you are very tech savvy and when you have the device with you. And the problem is in the internet, when you are talking to some backend service, then it's probably a bit complicated for you to go into the data center, build this room around this, or this special setup with this one server. Maybe it's even not a dedicated server, but there are other services running on the same server, whatever. So verifying that the service itself is really just doing what it does without going there is traditionally, very complicated. And just you can make audits, and the service provider can say that it adheres to regulations and did some audits and is compliant with X and Y. But it's not every service has those claims in the first place if it's not necessary around healthcare data. And then you simply cannot mathematically verify that their claims, how they use their data, is correct, adhered to in practice.
Trust is needed.
Trust is needed.
Trust is needed to some points. And even if I had these audits and certifications in place, what happens when I want to make a new version of my software?
There needs to be maybe a new audit.
Yeah, exactly. That's how it should be. So, so the point is exactly, when they talk about supply chain hacks, when some software in the whole supply chain, maybe some open source library has been compromised to do something it's not supposed to do. And it becomes a part of my software, then my software suddenly also becomes vulnerable. So in that sense, it's also hard for the service providers because they need to convince everybody else that they're being nice too. So yeah, the key point is here that it might be that I audit, I check this version that's running today, but how do I know that tomorrow you're running the same software? It's
yeah. So it's this, theoretically one could go there every day to the data center, but it's just no one does this. Yeah.
Economically, it doesn't make sense either.
Exactly.
So this is what we're talking about today mostly. This is the fundamental problem that computers often operate on trust. We assume that the people who we have agreements with are running software in a way that we assume they do, that there is some hope. For many software systems, like if I'm running a computer game, it's less important, although likely people would want to play a game only if there are not many cheaters. Agreed. But for some information, this is more critical. And we need to know that the other side won't do something with my data that they're not supposed to. So this is, I think, a good time to start pivoting to the topic of the day, which is trusted execution, or as it is also called, confidential computing, trusted platform modules, secure elements, enclaves, and I think there's a few more names. So there's a whole plethora of technologies which try to achieve the same thing, which is create something I think they call a trusted computing base. So what is that?
You mentioned that there are a lot of different approaches to trusted execution environments, and so my area of expertise are specifically now such technologies which are easily, air quotes, easily programmable by developers, and for general purpose applications. So there are, what I mentioned on your phone, there is a trusted execution environment. This is you can't really tap into it when you write your Android app, but what I used now, or have more hands-on practice, is those which run somewhere in the cloud, or at least today, and you can just put your software into it, and it's in its core, it is like a sandbox. So you have software inside of this trusted execution environment, and this software is then protected against the hosting environment, and you can remotely attest what software runs inside of it. What we were talking now previously in the introduction, that we want to get some assurance about what software is actually running inside of the trusted execution environment. This is this remote attestation capability of those TE technologies. So thing is that and this is for me like the most critical feature of TEs, that you can ask for a cryptographic piece of evidence. It's a signature in the end, from the software which runs inside of this protected sandbox, and verify this cryptographic piece of evidence, and in the end know exactly that the software is protected in the first place, and that and what software is running, or at least that the software that you are expecting is running inside of this secure environment. So and this allows you basically to understand that that the software, or if you know what software is running inside of it, then you can verify the software itself. You can audit the software and understand whether the software treats or operates on your data only in the way that you want the data to be processed, and that the data is not sent anywhere else in the internet or processed in other ways.
That's the big story. So let's unpack this a bit for people not accustomed to hardware architecture. So we're talking about processors and processing units that run the software code. Usually it's them that have this trusted execution.
Yeah. So usually, it's CPUs which have this technology. So
when you ask them to add two numbers, then CPUs add two numbers.
Exactly.
When you want to add two numbers that you would with your calculator otherwise, but you decide to use Intel processor for it, then what sort of happens if I want to add the two numbers? What does this trusted execution give me?
Okay, well, it adds two numbers. But now the cool part is that it ensures that the hosting environment cannot see it and also cannot manipulate the calculation. And I can verify that exactly those, this calculation has happened. When I uploaded the two numbers in the first place to make this sum or calculation, then I know exactly how my data was used in what operation. So yeah, it's no one else can see what happens inside of it, and I know exactly what happens with my data.
Okay, so let's. That was a good example. Let's role play this. I am a user of some sort of, let's say, some health application, and I want to send in my sports session data, my heart rate sequence to an algorithm that would tell me that maybe it's too high or I should be worried or there are some rhythm issues or something. And you have that algorithm on your server. So I have an app. I got it from my watch or my app or something, recorded this, and I have a heart rate sequence. So now you have a service, and if you are using trusted execution, then I can... Well, how this usually works is I get an app and I say upload data, accept terms, and then I get something back. With trusted execution, I could do something similar, but I could likely do something else too. I could get something more. So, for example, I don't know, can I get, before I give you the data, how can I know that you're you? You're the right person I should talk to. What do I need to do?
When you mean...
before I give you the data.
Okay, you want to understand whether the software is the correct software on the server.
Yes, that I'm not talking to some other system made by somebody else.
Well, that's technical. So if you didn't want to go into the technical...
No, I expected we will do the technical part, but again, so in the end... if I can do this, this is sort of a big deal. Because today I just upload my data and it's fire and forget, and maybe I get something back, maybe I don't.
Explaining the remote attestation process then basically is how to unpack it. So let's say what you get when you ask the server what software is running. So you get a bunch of hashes which are signed. Like this is what you get: a bunch of hashes, a bit of more metadata to understand what's the platform and the signature. And these hashes describe the state or the it depends a bit on the TE technology, but it describes basically what software is running inside of the system. So all this let's just say software. It's a bit more detailed, but let's just say software. It's just hashed. Basically this whole software is big. Some software is very big, and it's all compressed into a very small hash of 32 bytes length. Anyway, and this, it's a cryptographic hash, and you can't or at least with today's knowledge, it is not possible to in finite time to or in reasonable time to create a similar hash with other created from other data. So when you have this hash, then you know, or you can wait. Let's start from the other side. Then now you have the hash, and what you need as well is like a description of what software is running inside of the VM, or sorry, in what's the protected software inside of the TEE. So you ideally you have some build process for the software which takes the source code of as much as possible of the components, and then takes the source code and compiles it into this big software bundle, which was the thing that got hashed from the server side. And so now you take the hash which you got from the server and the hash that you calculated yourself from the compiled software, which you compiled yourself, and compare them. And then you know that, or can verify that exactly the expected software is running on the server. If the hashes mismatch, then it means that the server is actually running, or the service is running some different software, and maybe not trustworthy.
Okay, so it seems that there's a bit of work here. So before I send my data to you, I ask you, prove to me what software you're running, and then the processor, not your software, answers me, right? It's sort of like a driver in the system. It's if this is set up correctly, then this is not the software that some service provider wrote, but it's something more in the system level.
Well, it's very it's a multi-step process. So it is the software which the service provider coded, which answers this remote attestation request. So this gets the request that some user wants to do, or some remote entity wants to perform remote attestation, and then it asks through the TEE platform that it wants to get this cryptographic proof. So it goes it goes to somehow through the TE platform, probably into the hardware to acquire these hash values. So and the signature which I mentioned, the signature over these hashes, they are created by this TE platform. TE platform. So there are various implementations out there how this is done, but for some it's done by the hardware. Today anyway, it's always a question whether something is hardware or firmware or software. So anyway, that's why I like to just say the TE platform, because it's a mix of everything. So yes, the TE platform does or signs it, and then this signature and all this meta information tells me also what is the TE platform itself. And so this it tells me what type of CPU I have, and also what is the patch level. The TE platform also needs updates, software updates, and this whole remote attestation data which you get also contains information about that. And so then you ask the TE vendor, so for example Intel or AMD, for some additional certificates, which it's the signature is part of a longer certificate chain, and then you can verify via this certificate chain this the signature, and understand whether the platform is trusted. And then when the platform is trusted, then you can trust that this signature over the hashes is also trusted. So you can trust that the software inside of it, you trust the hash, then you have the software, the source code on your own side, and you know what software then is running inside of the TE, and then you understand that the endpoint to which you are talking inside of the TE, which produces this remote attestation, it's called a quote or report, one of those two words, I always mix them up, this remote attestation information, that this is like also genuine. So there's some additional data usually part of this quote, and this is in the end like this brings us actually to a third pillar of trusted execution environments. But yeah, this whole trust chain is basically you have some root certificate from Intel or AMD, and you have this signature created by the platform, and you have this the source code of the software inside of running inside of the TE, and then you can bring those all together and verify whether you can trust what's running in there. It's with everything there's more details to it, more complications. So for example, how you verify actually that the BIOS or UEFI firmware is actually up to date, and so more details, but just yeah.
If I got this right, then before, again, we discussed previously, trust is a hard problem. Trusting computer systems and services is something we couldn't solve before. The only way you could do it is by trusting that there's somebody on the other side of the internet is doing something as you agreed. So this looks complicated, but it seems to do some things that you can't do before. So if I read you right, then what I can do before I give you my sensitive health data, I can check that you are running a computer that has a trusted execution environment, because Intel signs off on that, or AMD or whoever made this computer is willing to say that, yep, I'm willing to give a signature that this response was given by a computer that I made. So Intel is willing to agree to that. Then you know that some part of the software running on then I will know that some part of the software running on your system runs inside this trusted execution environment. And I will get a hash of that software, which I can compare to maybe some nice people who have made an audit. I hope that
this is more realistic.
Yeah, because I'm relatively good at computers, I would argue. But maybe it's better if somebody who has more experience and the bigger team looks at the software and says that, yep, this is indeed an algorithm that does something meaningful on heart rate data, for example. So I will know that you're running a computer that has a trusted execution environment, and I know that inside that trusted execution environment, you're running a software with that hash. And I can ask an auditor to say that, does this hash belong to a system that you audited and feel that is trustworthy? And if they say yes, then I know that likely if I send you something, then it would go to that trusted execution environment. We'll get to that soon. But can you fake this to me? So what is preventing you as, or someone, evil twin that you don't have, from faking that you are running a trusted execution environment to me? So can you just send me some hashes and hope that I will believe them and still send you my secrets?
Yeah, so no.
That's good. Why?
well, the no is actually not 100% correct, but it's 100% correct for the practical cases. Well, okay. So anyway, thing is, the CPU contains a private key, a symmetric key. It should be symmetric. Anyway, a key, and this key is known to the CPU, and it is known to the vendor, software vendor. So, for example, in the case of Intel, they have a special air-gapped facility where they store this specific private key or secret key in a secure manner, so that hopefully no one can access it. And it's especially I think it's air-gapped. So that at least through the internet, no one can access this facility. And when you now do this remote attestation, then this whole certificate chain, what I mentioned, then this whole certificate chain is based or it uses this secret, which is known to the CPU and to Intel. And this secret is used to derive, in a complicated way, another pair of public-private keys, which are also part of this signing chain. And anyway, it's just this that Intel knows exactly what keys are valid, and if one of the TEs uses such a valid key during the remote attestation procedure, then with the help of Intel's or the TE vendor certificate infrastructure, you can identify that a genuine secret key was used there. So basically, this implanted secret key is this whole magic, I would say, behind this remote attestation procedure or feature. And so when I now fake this with I use some other chip which doesn't have this TE technology on it, then I don't have such a key which is registered by Intel or at Intel's facility, and so I can't fake this signature. There's no valid certificate chain path here.
Okay, so cryptography to the rescue again.
Yeah, it's cryptography from beginning to end, and even on the outside. There's just so much cryptography, and the cool thing is that it's all at least for the end user, it's at some point a lot more automated. So I don't need to go to the data center to validate that the software is valid, but I just get this hash in the end and can make this from the distance this check. And
that's exactly what I've liked so much about trusted execution. You suddenly can start interrogating other people's servers on what they do. Okay, next up, I've decided that you're trustworthy. I can send you my data. So now I send you my secret data, and then you process something on it. So can other software running on your servers get my data as well?
So when they are not inside of the same TE, and you programmed the TE correctly, the software, then no.
But that here is the part where the audit becomes important. So everything that has been audited, everything that's hashed, this is all allowed functionality. But everything that's not under the same hash, that software can't get access to my data.
Yeah. So exactly. So the point is, that the TEE technology creates a barrier around the protected software to shield it from the hosting environment. So usually a server runs in the cloud a hypervisor. So this is something like an operating system, but a level deeper, and which juggles all the VMs and and this usually has, in traditional sense, it could look into all the VMs which are running there. Cloud service providers usually they have no interest in this, because if they spy on users' data, then tomorrow they have a lot of spare hardware to mine bitcoins. But exactly the point is that there could be co-located VMs, which might break out of their VM and then infiltrate the hypervisor. So this whole TE stuff is it's a security layer or on top of your existing security layers. And what it provides is this cryptographic barrier. So the software and its memory, the working memory, is encrypted as well. So the key is hidden inside of the CPU. There's no no legit API to access any of the keys. It's all inside of the CPU, and it manages transparent encryption, decryption for the protected software itself. But software outside, when it wants to access it, then either it can't access it in the first place because then there's some access violation stuff, or it would just see noise, the ciphertext. It's the software is protected from everything that runs outside of it, at least on a software level. So on a hardware level, this whole protection is also nice, because if, for example, someone could break into the data center, rip out the RAM slots or RAM sticks, and do those so-called cold boot attacks, then they also can't access any data inside of the VM which was used by the VM, because it's encrypted.
Okay, so if I'm another process running on the same computer, if I'm running outside the trusted execution environment, then I look at memory and it's all encrypted to me. And even if I'm running like with administrator access or root access or system user access, then this thing is happening several layers underneath me still.
Yeah.
Okay.
So it's this turned around sandbox. So traditionally, the hypervisor wanted to be protected from the VM. Because you don't want in your cloud environment, you don't want any customers to break out of their VM and to break into other customers' VMs. But now it's turned around that the VM now does not trust anymore the environment around it, and exactly.
VMs are virtual machines.
VMs are virtual machines.
I just noted that we might not have said that, but when somebody says VM or virtual machine, then think big blob of software. Yeah, that's hopefully helpful, like a full computer worth of software. Alrighty, then I can send you data, which because I ran remote attestation on you, I know that you're running software and hardware that can protect it. Now I give you the data. Now, if you want to run your code on it, you just use this trusted execution to run the piece of code on my data, and you send me back the result.
Yeah.
And we're done. Value has been created, and GDP increases.
Yeah. So there's steps missing.
Likely there seems to be. Again, this seems like a very complex technology. So we likely need to dive into how easy it is for anybody to use it. But first of all, is it? We talked about hosting environments. These are, think like somebody else's servers, like clouds are usually the hosting environments or like machines. So are there, how available are they? So if I want to run software using this technology today, then do clouds support this?
Yeah. There's a multifaceted answer here. So I mentioned this Intel SGX in the beginning. This is an older technology, and this is kind of more mature. And there are multiple cloud service providers which provide SGX capabilities, also integrated in other services. So it's very comfortable to use, or you can just build your own custom service custom software for Intel SGX and run it there. So this is rather mature, I would say. And then the newer TE technologies, which are VM-based TE technologies, there it's a bit more complicated because the technology is still rather new. There are at some cloud service providers, they are in beta stage, so they're not fully like production ready, but they can be used and tested and all. Some cloud service providers have them just as usual offerings, and it really depends, where you go and what you want to do specifically. So when you just take your or rent a bare metal server, this is usually the more expensive option in the cloud. You get just basically a physical server for your own use. Then in principle, it's as production ready as you would get now an Intel server to your home and would use it. But then that's it's not the most maybe beginner-friendly way to get started with TE technology. So what cloud providers provide are those so-called confidential VMs, where you can just tick a button or tick a checkbox, and then you get this TE protection for your VM. And this is a bit, not everywhere in the 1.0 stage, and especially because it needs to be super beginner friendly usually, and as you as I try to explain, this whole remote attestation stuff is rather involved and has complications here and there, and they try to adopt it into their cloud infrastructure, and then it just takes time to get mature.
Right.
To become mature.
The infrastructure is out there. You don't need to buy your own data center, but if you do it, then you can get it for sure. So the servers are for sale. This is not research grade technology in that sense, for sure. Right. So okay, let's look at the software maker, app maker side now. If I actually wanted to make this app, or I would actually want to make this heart rate analysis service, then how do I get started? So what sort of, can I just convert my Python code or TypeScript or whatever code into something that runs on SGX, or how do I make my software run on trusted execution?
Okay, maybe before you do that, you should understand what's your threat model.
Good point.
So thing is, in the beginning you mentioned the game server or something.
Yeah.
So if you have a Minecraft server and just want to game with your friends, maybe just skip TEs altogether. It's not worth the hassle. But if your friends, whom you want to play Minecraft, are actually super VIPs, maybe you go the TE route. And when you now understand that you need a TE because of its additional security properties, then it depends a bit on the software architecture, like what your piece of software, how it's built. And the easiest answer to this question, how do I move my existing app into a TE, is to use these newer TE technologies, which are those VM-based technologies, because it's in the end just a VM. You just throw your code in there, your software, and then you boot it up, and you can do remote attestation if it's integrated nicely with a cloud service provider infrastructure, and all is fine. And it can be as easy as this, but the devil is in the detail, and also why it's complicated is that usually the software, like for example, wants to persist data even when the VM maybe does a reboot or something, and then you need to think about how to protect this data when the VM is now, or your software is not around, because this whole protection of the software and its working memory is at least for the newer ones, or I have mostly experience with Intel TDX now from the newer generation TE technologies. The protection goes from the boot time or boot up moment from the VM to the when it shuts off, and afterwards the TE protection is gone. And so you need some other security or protection measures for any persisted data beyond the lifetime of the TE
database or files sent
exactly
on disk, or
what you store in S3 buckets, and you need to that there is, if you encrypted it, the encryption key is somewhere, and you need to think about where is this somewhere. And if you just think that I encrypt this with another key, then now you have this other key, and so it's that is a very hard part, and so why it also I think this is also one reason why it takes or it is complicated to like make a convincing story in the cloud, because usually you integrate the key to protect your data, which is persisted. You protect this key with the cloud's key management systems, or anyway with cloud solutions. But then your key is still in the hands of the cloud, and it's in the end it requires a thorough analysis of what are the threats you want to protect against, and what are the goals you want to achieve, and what is the amount of pain you are willing to go through
to get the magical security results.
Exactly. And so there is no silver bullet here. TE technology itself it's very cool. I love it, but it's no silver bullet. And when you want to get started with using TEs, then really the confidential VM offerings in the cloud are one very good starting point, I'd say, to just get your toes wet, or how you say it.
Yeah, toes wet is.
Yeah, and then but it very depends on your use case, and it might be that that you actually want to use Intel SGX for its specific security properties, and then you could Intel SGX is maybe I don't go this route anyway. Yeah, so it's there are ways here and there to get your software into a TE. If you have existing software, the easiest is the VM way. Yeah.
Okay. If I have my existing service side, all my backends, all my databases, and I somehow manage to do this key management thing, I figure out how to do it properly, I get the right that part I might need to change about my software, I guess, and to make sure that whenever I store my keys is actually a good key storage situation. But I think cloud providers offer you components for that these days too. No?
Well, there are. I think it's mostly integrated into like the existing cloud provider key management systems. So I'm not actually sure. How like whether there is some changes which are now specific for the TE offerings. I think maybe it's integrated in the access. You can specify in the key access policies that only the confidential VM is allowed to access this key. So you can do that. Should be like this.
We're not directly here, let's say, advocating for specific software products or services, but there's likely that there are vendors who provide components for this. So if anyone wants to find them, then go and see the internet, and they're likely there. But where I wanted to go with this is, assume you do this, you convert your server side to run on a confidential virtual machine. So as the service provider, what do you gain from this? What additional security guarantees you get that then you can go and tell your CEO that I did this?
Depends on how you use the TE. So if you are the service provider and want to provide just more security to your service users, then this is the value you get. You can tell your users that they can attest the software that you're running, that they can gain more confidence. Maybe that the users know exactly what happens to the data. When you can or have this heightened security posture, maybe you can more easily comply with GDPR or some health compliance measures. So this is what you get, maybe unlocking other markets.
So I can tell my users that they don't need to trust me 100%. I can give them a tool for checking whether I actually run the software I promised to run. And if I upgrade the software, then they will get an error unless they start using the new hash they got from the auditor for the new software version. So upgrade management is going to be pain, but sometimes it's worth it. So that's a good justification, that think of your attacker model and think of whether your application needs to go through that pain. Okay, we have the users covered. Users can actually check that the service hasn't changed, the code hasn't changed, and it's still running the same thing. So nobody has snuck in another version. So this reminds me, I read that Signal, the relatively popular, exceedingly popular starting from this year with some endorsements from governments internationally, has used trusted execution to make set intersections of people's contact lists, I understand. So if I have a Signal account and then there's some phone numbers on my phone, then it can sort of match them to Signal users, and it's doing that inside trusted execution. So that was one of the more famous use cases of trusted execution that I know of by big production level. Do you have anything else that comes to mind that that's we could say that's famous use of trusted execution anywhere?
Well, every, as I mentioned, every Android and also iOS device has trusted execution environment. So I think this is a very great success story. Now for cloud services, so there are stories, but I don't think that they're big or big. I mean, it's all in their niche. So, for example, in healthcare, there were various uses of TE technology to go through lots of personal healthcare information records, and those are success stories. But they are, we had some projects where we used it, but it's. I would say the Signal one is, at least from my perspective, the most prominent.
Yeah, prominent. Yeah, that's good. That's a good point. So it's again, it's a great example of technology that gives you guarantees that you couldn't give people before. You can bring about new services where cloud server provider can't get access to your data, where you can give your customers tools to make sure that your software is doing exactly what you're supposed to be doing. And all this is now possible if you're willing to jump all these burning rings of fire of engineering all this properly. So this is something that I think should have quite an interesting future. But the question is that can we fully trust it? So I have heard about side channel attacks, and I think it's only fair if we tell the people what these are and how much and when they should worry about this. And I guess this comes back to the attacker model.
Okay, let's define what a side channel attack is.
Good idea.
So I have a problem with chocolate.
Okay.
So when there's chocolate in the house, I eat it. No chance of not eating it.
I didn't bring any.
Thank you. I'm really thankful for that. And so once we had a big bar of chocolate at home, and I ate already too much, and there was more than half of it still there. And so I told my wife, please, for the love of God, put this anywhere in the house where I can't find it. And so she took it, went to the neighbor room, opened some drawer, put it there, closed the drawer, and then I went to the same drawer, opened it, and told her, no, please, like really hide it, and so that I don't understand where you put it. So the thing is, I did not see where she put it, but there was so much. It took her 5 seconds, so she couldn't go anywhere far in the house. Like it couldn't be in the basement, for example. And I heard the actual sliding noise of the drawer. So it wasn't like a door. It wasn't under some blanket or sheet or something. I could, without seeing, know where she put the chocolate. Okay. And the place of where the chocolate is hidden was basically the secret. And CPUs are no different, actually. Okay. So,
actually, this is CPUs, an amazing example. I've never thought about it like this.
CPUs don't hide chocolate from me, although I would be thankful for it. But when a CPU processes data, then it tries to do it as quickly as possible. So the CPUs are optimized for execution time, and this is counterproductive for cryptographic operations, because in cryptographic operations you actually want an operation or processing of the data which does not change. It's not observable whether I process something which on a binary level just consists of ones, or something which just consists of zeros. But as it turns out, CPUs actually, for example, consume a different amount of electricity to process data which has a different amount of zeros or ones. And very famously, or at least in cryptographer circuits, is asymmetric cryptography. So I think one of the first side channel attacks was actually that the server had it used RSA cryptography. So there's just the classic algorithm for asymmetric cryptography, very used or widely used when using just connecting with HTTPS to any servers. Then the older side channel unaware algorithms, they use some rather primitive algorithm, maybe optimized for speed, which does some shortcuts when depending on how the number looks like on a bit level. And you could then basically the remote user could just send 1,000 queries there and measure how long it takes for the server to respond and get some understanding of it. And based on this varying execution times, it could restore like the private key, like what bits it consisted. And so this timing side channel is very classic. But yeah, it's just one. The electricity side channel I mentioned is one. Then you have CPUs they're enormously complicated, and they have all kinds of tricks in there. So there are some caches in the CPU which might allow other software running on the same CPU to deduce or infer secrets which are processed in the other process running on the same CPU. So there's when things are complicated and people are very creative, then they find ways in the most crazy ways to exfiltrate some secrets from other processes. So these are called side channels, and the problem is this is oftentimes actually rather complicated. The chocolate example, it was easy, but only because my wife wasn't aware that I'm really, really hungry for chocolate and really listen to where she's going. And back when the RSA side channel was discovered, then people were just, I think back then they were rather unaware of these kinds of attacks. But yeah, I think it was like this, that they were that rather unaware back then. But now people are a lot more aware of this. There has been a lot of research. Researchers up to this day try to find new side channel attacks, and it's becoming very hard. Especially TE technology also has been very much under attack. Every side channel paper has they also verify whether it works with TE technologies, and if it works with TE technologies, then they have a special section that TE technology X is broken, or something like that, and it is they are complicated today, so it's hard to find them. You have to have a lot of expertise with this technology. You have to have a lot of creativity, so you can't just start today and in 2 days you have an exploit ready. It's very it requires lots of testing, lots of experimentation, and yeah, just expertise, luck. In the end, a lot of luck, and then when they were experimentally tested, they are tested under lab conditions. So it is, they exactly set up the CPU and the software on it to facilitate this attack, this side channel attack, to make it successful. And it is in practice a lot harder to actually mount such side channel attacks. So an attacker, for example, if you are running this confidential VM in the cloud with your software, and you don't have exclusivity on the physical server, then the attacker must manage to get on the same physical machine, and then they must do lots of measurements or these, however they attack it. They usually what is attacked are specific gadgets, or it's called gadgets. Some specific instruction sequences in the code which can be attacked. And so the attacker software needs to wait until this specific sequence of instructions is executed, and it is just very, very complicated to actually attack, mount an attack. And when you actually have an exploit, then probably this side channel attack was already patched by Intel. So usually there are microcode updates which circumvent any users. There have been some where actually the actual solution was to build a new CPU, but Intel does so every once in a while, and yeah, but then it's some. There have been then software measures, so the software running inside of the TE need to be built with some specific flags, and so to have some counter measure. And what this means for the practical user, if you have data which is so valuable that you need to be aware of side channel attacks, then you probably know it already. Then you already have such a tower of software protection layers or security protection layers in your stack to protect your data. And then you are aware that those exist. Then you might have strategies to protect against them, make it harder to mount them. And then you are also aware that TE technology is just another layer. It's not the final layer. But if you today don't know, or if you just have your service and side channel attacks up until now have not been a problem, then I would argue, but ask your doctor, that they are in practice not a real threat. But tomorrow there could be a new side channel attack which nullifies my statement here. But I would say that in practice, Intel does a very good job, and all the other TE vendors.
This is a moment where I think we have to make a small side remark that Cybernetica has made a research report series on threats to trusted execution systems, so collecting the knowledge and collecting research and papers on it. So this is something you can find in the Cybernetica's research report series, and you've also co-authored that report. So that's something that we have available. Right, so we had to talk about side channels, because otherwise all the people who write side channel attack papers would leave us comments saying that why didn't you talk about side channels? So
yeah, maybe I also then talk about some rather successful side channel attacks. There was one where I think it was from a paper called, was it SGX? Like AXE or SGX.fail.
What you break wood with.
SGX or SGX.fail. One of those two. They were using specific problems in in TE technologies, and I think they used some side channel attacks, and back then problems in the time frame from vulnerability becoming public to vulnerability becoming actually patched in this specific type of server. Intel releases, or the TE vendor releases a patch to the firmware, then actually the hardware vendor or like the server vendor, which packages those, they also need to do their own testing and packaging and then send it out to customers. So it actually can take some time. But there was research which showed that there is a gap, or there's a problem, and so Intel reacted. But anyway, what happened there was that there was some blockchain system which was built on Intel SGX, and there was some rather important root key which was duplicated or replicated on all the nodes, so that they could participate in this blockchain. I think it was a blockchain, and the researchers could exfiltrate this rather important root key. And in another case, it was, I think, some decryption key for Blu-rays. So there was some Blu-ray software and which used SGX, and they could exfiltrate this key. But yeah, there also a problem was that actually a reason why I think this is now a bit more complicated, maybe for the technical users. So Intel SGX started on consumer laptops. So my Cybernetica laptop, which I have, it has Intel SGX support, old one. And thing is, users I have a Linux system, might not tend to update their BIOS regularly. But this means when they don't update their BIOS, that the SGX protection might have holes, because it depends on up-to-date BIOS. And if now some big software, a Blu-ray player, some Bitcoin network which has to run on a lot of computers, when they would all require their users to regularly update the BIOS, then probably the user would use some other software. And so they decided to have some slack there and allow also some kind of unpatched systems. But this means that one can attack the systems when there's enough time. And so today, Intel SGX is no longer available on consumer hardware. It's just in the server landscape. And on the server landscape, usually, it's easier to update the BIOS.
But if a server is running SGX, when my computer doesn't have to, I can still run at the station, right?
Yeah, exactly. So this is the really cool thing. In principle, you can run at a station in the browser.
Right, that's cool. All right, let's tie this up then. Do you think this technology will make it? Will we see more of it in the coming years?
Yeah. Speaking out of my TE bubble, I hope so, because I think it is at least it always provides some additional value, and I think it should become kind of more standard in the cloud. So just ticking your TE checkmark in the cloud, I think maybe in some future there's no checkmark again anymore. It's just confidential VMs.
Computing for all virtual machines.
Yeah. So there is reasons why this might not always be, good. At least for now, there are, for example, 1 or 2% performance overhead with TE technologies, something around those numbers. But it depends largely on the workload, and right now not every CPU deployed in the data center has this TE technology, because there are also older generation CPUs there. But I think maybe in 100 years or 10 years,
then we'll have quantum computers maybe.
Exactly.
Yes.
Yeah. But I think it becomes a lot more like widespread in some domains. It becomes just the default. Just check the or tick the checkbox, and then it's all good. And but also right now the software is rather bleeding edge. So usually you don't just start writing your own software for this for some TE technology from the ground, but use some framework where you can more easily integrate, and they are rather bleeding edge right now. And so we have to see how they turn out, like how user-friendly they turn out to be. So because right now it is a complicated process, depending on what you want to do, and but there are rather low-hanging fruits. So I know what. Do we have time to?
Let's see if you have one great example.
Okay, well, let's use two. So the easiest, in my opinion, use case is this lift and shift. You have software which runs on your on-premise, like at home, and you just want to move it to the cloud. Then actually this is super simple, and like the prime use case for confidential VM technology. Just put it in a confidential VM, and you have more or less same trust relation with the software running in the cloud compared to when you run it at home. And this is super easy, but something which we did was where we have like multiple users participating like jointly in some computation to I have some business secrets, you have some business secrets we don't want to share, but we can put it into a TE. Then this is like we try to make it super user friendly. We're on the way there, but there are just still hurdles, and I think this will become a lot more streamlined in the future, and hopefully, like it will never be a one-click solution, but it will become more easily and more transparent.
I guess that we both have to do the attestation if we both put our secrets in there. Yeah. So
everyone has to attest. So
that's the only way.
Just,
otherwise,
brush your teeth in the morning, do your attestation.
Exactly. So, right. Let's stop here. To a future where people attest as often as they brush their teeth. I've still Dan today together with Armin, and until next time.